Implicit differentiation. Another tool we can use. So we've got all the stuff that we went over at the end of the last slideshow, but now this is something new, and it allows us to take derivatives in a very specific scenario. So only really two things to worry about. One is implicit differentiation, and for the love of everything holy, please make sure you understand the difference between there, and there. Okay? It's just, there's no excuse for it. Blah, 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 blah. Okay, before we get into this, what is implicit differentiation going to do? Well, if we have a function like y equals 2x plus 3, we take a nice simple linear equation, it's already solved for y, so the notation of dy dx makes perfect sense. For those of you that are visual learners, let me write that down. You must have a great. It's not been one of my better periods. There we go. Let's try that again. Okay, so if we have a simple function like y equals 2x plus 3, it's a linear equation. And when we take the derivative, again, remembering the notation dy dx would be equal to simply 2. No problem, right? Because that notation says take the derivative of y with respect to x, where x is the variable. What if you have a function where you can't solve for y? In other words, we can't get something nice and pretty that says y equals all this other gunk. The y's are mixed in and it's too mathematically difficult to solve for y. Implicit differentiation will allow you to do that. That having been said, take a look at the steps. First of all, you're going to differentiate both sides. It's not going to be nice. It's not going to be like y equals and all this other stuff. It's going to get a little ugly, and I'll show you the process as we go through it. Then you're going to take all the dy dx's and move them on one side, take everything else and move it to the other side. Then eventually you're going to solve for dy dx. Now we're going to simplify things a little bit. It gets to be a pain to write dy dx out every time, so we're going to use y prime. And again, this will start to make sense as I go through some examples. Okay. Are we good? Take the derivative of both sides of the equation with respect to x. Get all the dy dx's on one side. Factor out the dy dx's. Solve for dy dx. What you're left with will be the derivative. And it really isn't as bad as you think. We just have to be careful to do a couple things. There's a lot of algebra here, not a lot of calculus. Okay, we good?
Yes.
All right. All right. Here we go. Yeah, here we go. Okay, there's that guy. Now, notice what's going on there. I have no idea how to solve for y in this case, and you shouldn't either. And if you do know, there's something wrong with you. So unlike the function I talked about before, since we can't easily solve for y, we have to use implicit. And here's how it works. We're going to take a derivative, but you have to remember that our variable is x. Okay. So the one contention we have for that is that when you start to take the derivative, you take the derivative like you normally do, but if you take the derivative of anything that doesn't have an x in it, you have to include a prime. Okay. So as I start doing this, I would get the following. The derivative of y cubed would be 3y squared, treat it like a normal derivative, but there's no x there, so I have to attach a y prime to it. Okay. Which means I took the derivative of y, but I didn't take it, I took it with respect to x, so you attach a y prime to it. Go to the second term. Derivative of y squared is 2y, but again, no x there, so I attach a y prime. Derivative of negative 5y is negative 5, y prime. The x's are just treated plain because that's what we're doing, so you just get a negative 2x. There's no such thing as an x prime in there. And please, what's the derivative of negative 4? 0. Good. That will trick some people. I'll get things like negative 4y prime or just negative 4 or all kinds of other things. Before I move on, are you okay with that process? Anytime you take a derivative of y, you just attach a y prime to it. Take a derivative of x, just like you normally do.
So is y prime a substitute for x?
Y prime is a substitute for dy dx.
Okay.
Yeah, because I don't want to write, if you want to write dy dx every time you can, but y prime's a lot quicker. So that's step one. Took the derivative of both sides with respect to x. Then get all the y primes on one side. They already are, but move everything else to the other side. So 3y squared y prime plus 2y y prime minus 5y prime is equal to 2x. That's step two. Step three, factor out a y prime. And the last step, step four, is to solve for y prime. How do I solve for y prime here?
Bring everything over to the
Yeah. Divide by that big chunk of thing. I didn't think that would be such a difficult question. All done. Okay, so now we have a value for the derivative, which is a little weird because we haven't had derivatives before that have y's in them. We'd always get a y prime equals and a bunch of x's, but that's fine, that works. Then you go further and say, okay, well, what's the slope of the tangent line at a certain point? Well, the difference here is that now when you deal with a certain point, you've got to plug an x and a y in instead of just an x. Everything we've done up to this point has just been x's. Okay, but there's the basic process. Are we okay with this?
Yeah.
Good. All right, let's move on then. How about the second derivative? This will be fun, right?
Of the one we just had.
Yeah. Because we took the first derivative. Let's find the second derivative. You ready for this? Quotient rule. So let's take, I'm going to do this. I'm going to bring this up here. Y prime is equal to 2x over 3y squared plus 2y minus 5. And then I'm going to erase this mess. Now, I will say that a lot of times if you're checking your answers in the back of the book, Bob is very simplify happy, meaning he likes to take things down and break them down as much as possible. That's always not necessarily the case, and you'll see what I mean in a second. Okay, so following the same rules, I can't solve for y. I'm looking for the second derivative, so I start the same process. What's the derivative of y prime? Y double prime. And I think, Connor, you said it, we have to use a quotient rule here. Big gazintabar. 3y squared plus 2y minus 5, quantity squared on the bottom. Bring that up on top, 3y squared plus 2y minus 5. Times the derivative of the numerator. What's the derivative of the numerator? 2. Minus, big brackets. The numerator times the derivative of the denominator. Okay, so, Maggie, what's the derivative of the denominator?
6y plus.
Nope.
6y y prime.
There you go.
Plus 2y prime.
Well done.
That's
That's it?
yeah.
Okay, close parentheses, close bracket. Okay? Leave the denominator alone, clean up the numerator. So I got a 6y squared plus 4y minus 10 minus 12xy y prime minus 4xy prime all over 3y squared plus 2y minus 5 quantity squared. How are we doing so far? Okay, ready? Okay.
In the brackets on the numerator, why is it 6y y prime and 2y prime?
Took the derivative of this, which is bring it down, so 6y. But because I took a derivative with respect to y, not x, you got to attach a y prime to it. Same thing here. Derivative of 2y is 2, and then you have to attach a y prime to it. Okay, you want the good news or the bad news? Good news. That looks pretty good, right?
Yeah.
Yeah, the bad news is we can do a little bit of a substitution there.
Is it necessary?
Maggie just summed it up for us. Any idea what substitution I can do?
Oh, I don't know. No.
Right. Mark?
You have to put that whole y prime in for y prime in the equation.
He says that with such a look of terror on his face. It is a possibility, yes. And this is what I was talking about with Bob. Bob is not going to be happy with its answer. Okay. Bob is then going to say, hold on a second, I know what y prime is. Y prime's right here. So let's take that beast and put it in there and put it in there. Now what's going to happen? Number one, it's going to get uglier. Number two, we're going to get fractions within fractions. Guess what is never acceptable? Fractions within fractions. So just visualize in your mind without throwing up how nasty this is going to be. Now all of a sudden you're going to have a fraction within a fraction with that as a denominator. So what do? You got to get rid of it by multiplying by this denominator over itself, because that's equal to 1, doesn't change the value of the equation. So then you multiply everything by 3y squared plus 2y minus 5. And it starts to simplify this, but now all of a sudden that'll be not bad, because that's going to simplify and that'll go away, and then you're just left with that and that. But now all of a sudden you got each of these beasts, multiply that by that denominator, and then all of a sudden you got one down in the bottom, so that squared isn't squared anymore, it becomes a cubed. At that point, when you're done crying, you just sit there and give up. Okay? Why would we do that? And the answer is you wouldn't. Okay. So, let's suppose you're thinking, okay, well, I've got a second derivative, and now I want to know something like, what is y double prime, y double prime of 2?
Oh my gosh.
Okay? So, if I'm looking for y double prime of 2, that means I need to plug 2 in for x. It also means I need to plug a value in for y. Where would we get the y value?
Nowhere. When you plug it in, y.
You would go back and figure out what the y value was of all these. So, my point being, if we're going to plug in a point, why plug this monstrosity in here for the prime? Why not just plug the numbers in here and get a numerical value? Okay, in our original function, I don't remember what the original function was. That guy?
Yeah.
Oh, I don't even want to solve for a point on that. Let's see. Let's make y 0. I like y being 0. Yeah, y is 0. So 0, 2. Hey, let's do that, kids. Let's suppose then we're wondering what's the second derivative at the point 2, 0. Okay. Now, why 2, 0? Because I know that's a point on the original function because I cheated and made it nice.
Thank you.
You're welcome. I don't want to bother putting this monstrosity in here because then it starts that snowball to hell. Okay? So, therefore, I'm just going to take 2 and 0 and plug it in here for x and y and get a numerical value, then take that numerical value and plug it in here with all the other x's and y's. Does that make sense?
Where'd you get that value from?
I just made it up.
Oh.
I know that 2, 0 is, because I looked at the original function and I got ugly y's in there, so I made the y 0 so they go away and then solve for x and get that. Okay? So, my point being, we shouldn't have to do that, nor do we want to do that. We can do it, right? Because you're all mathematically solid here, but we ain't going to do it. Are we good? Greg, you got a question?
No, I'm
Just doing some yoga back there?
yeah.
Yes, sir.
Would the AP test expect us to do that? Or
No.
okay.
No. The AP test might expect you to find y double prime of 2, 0.
Yeah.
But again, if you use the numerical values, you'll be fine. I'm erasing. Are we good? Okay. What was that? Oh yeah, okay. I'm good. Now we take it a step further. There's a function. I don't know how to solve for y. I'm not going to bother solving for y. And when I'm done, I want to know the slope of the tangent line. So I have a point to plug in now. And so I did this example, or I chose this example for 2 reasons. Number one, it gives you an idea of what happens now when you plug in a numerical value. But also, we need to talk about this puppy. What's going to happen there? Well, let's do the left side first, before anybody freaks out. This guy needs to be done as a chain rule. because I got a function of the squared function, but then I got that mess inside. So I get 6 times x squared plus y squared times 2x plus 2y y prime. Let me give you a second there for that to sink in. Are you okay with that? Yes, sir.
I have an idea for the right side. Could you make a product rule with 10x times 10y?
Yes. The key there is product rule. Now, what you do with the 100 is entirely up to you. I mean, you can split that up however you want. I personally would just leave it floating out in front so it doesn't bother anybody. But if you want to break it up 10 and 10,
Or whatever.
1 and 100,
That works.
50 and 2, 4 and 25, whatever.
Plethora of options.
Well said, sir. I'll leave the 100 out in front if you don't mind. Why do we have to do a product rule there? Because it's two different functions. Even though the y is kind of wonky because it's an implicit differentiation, you still have to treat it as a product rule. Which means the first times the derivative of the second. What's the derivative of y? Y prime, very good. Plus the derivative of the first, uno, times the second. Yeah, believe it or not, that's the easy part. Max.
You don't have
You can if you want, but you don't
to.
have to.
No, I'm good.
I thought you'd see it my way.
Do you know what time this period ends?
No. Anybody know what time this period is?
About 10:38.
10:38. Plenty of time to enjoy your banana.
Thank you.
This will make no sense to anyone watching the video. Okay, so now we need to make a decision. And we're going to have Mary make the decision for us. Mary, would you like to solve that for y prime? Or, since our ultimate goal is to figure out what the slope of the tangent line is at 3,1, do you want to plug and chug first? Both answers are acceptable. It's entirely up to you. Don't feel any peer pressure from anybody staring at you in the back of the head to make sure you get the right answer.
I'm feeling it. Can I have my options again?
Certainly. We could take this and algebraically solve for y prime, then plug in 3 for x and 1 for y, and we're done with y prime. Or we could plug in 3 for x, plug in 1 for y, and then solve for y prime. We have our slope.
Tough option.
It is tough. It is tough. Your third option is you can have what's behind door number 2.
Is there an easier option?
Well, door number 2 would be the easiest option. But you don't know what's behind door number 2. Just be careful.
Can I do door 2?
You're gonna take door 2? Yeah. Okay, ladies and gentlemen, she's chosen door 2. Behind door 2 we have
That's door 2.
a giant stuffed banana! Congratulations, thank you for playing.
What's on the back?
There you go.
Is that your new book?
Again, not making sense on the video.
That's true.
Yeah, and James could be so
That's 2 references to bananas within like 2 minutes. Yeah.
I have a question. Where did you get this?
Why do you have it in the closet?
What else would I do with it? I forgot, I won that somewhere.
Does it have a name?
I hadn't named it until now, but seeing as it's now your banana, what would you like to call it?
Oh, that's a lot of pressure.
It is a lot of pressure.
Don't mess up. Take some time.
Yeah.
Yeah, think about it.
Let's just
You
spend
get
the rest
one
of the
shot.
We've got until, I'll give you 10 minutes. At 37, we're gonna need to know a name.
Alright, I'll
Okay.
do my best.
Don't
Okay.
let us down.
Wow.
Banana.
No pressure though. Jeez.
You better pick a good name. Oh, I got time.
Okay, so, now what? Second option?
Yeah.
Okay. That's probably what I would go with also. 6 times 10 times 6 plus 2y prime equals hundo times 3y prime plus uno. So that 60 is 360 plus 120y prime equals 300y prime plus a hundo. 180 y prime is equal to 260. So therefore y prime is equal to 26 and 13 ninths. Did I do my math right?
There's a chance.
Well, yes, there is a chance. I would argue that that's probably the better choice. Well, door number 2 was the best choice. That is the second best choice there. This problem leaves you some options. If it didn't ask you for the slope of the tangent line at the point 3,1, then you would have to take this monster and solve it for y prime. And notice, to solve this for y prime, you've got to do some distributive property first. Okay, so I would have to come down to, I'd take this x squared plus y squared multiplied by 2x. Take the x squared plus y squared multiplied by that monster, and you can see how ugly that would be. But again, you follow the 4 steps. Everything with a y prime to the left, everything else to the right, factor out a y prime, divide. And that ugly, nasty equation that you end up with is the derivative. Okay, but in this case, we're good to go with 13 ninths.
How
Question?
did you get the 100, the first part of that? Second part? That whole part? Yeah.
This is a product rule with this guy, because these are considered 2 separate functions,
Okay.
and it's a product. So that's the first times the derivative of the second. Derivative of y is 1, y prime. Derivative of x is 1 times y. Okay? Anything else on this before I erase? Okay. So try to be a little sneaky here when you're doing these and make your life a little bit easier whenever possible.